Hello, in this video we're going to look at calculating the moment of inertia. Let's just start with an example. We want to use that formula we ended with last time, that the moment of inertia for an extended object is equal to the integral r squared dm. And we want to use that to find the moment of inertia for a thin rod, pivoted about one end. So it's not just that particular shapes have moments of inertia, but shapes and pivot points together have a moment of inertia. If you take a rod and you swing it around by one end, that's harder to do than taking the same rod and swinging it around by its middle. And so different moment of inertia. We are going to make the assumption that the density is constant. In fact, density here is the key for solving this kind of integration, and uniform just makes it a lot easier because then the density is a constant. So if we made a sketch of our system, we'll have our rotation axis, and then we'll have our thin rod. Thin just means that its thickness is much smaller than its length, so that we can almost pretend that it has zero thickness. We'll call that the, not dx, but we'll call this the x direction, which we want to divide up into dx's. So one little slice of this would be a dx. And the whole thing will have length L. So the idea with an integration is to take your object and slice it up somehow. With a thin rod, we're going to make our slices in the long direction and assume that each slice is uniform. And then this thing would have some cross-sectional area A, which is not specified here, so we assume that if we use A in our calculation, it had better cancel out. That's kind of a sanity check here. But one more thing. We have dx, but that's not what we need. We need dm. What are we going to do about that? Well, the solution is to use density. So since density is constant, that's what uniform means here, the density, which is equal to the mass divided by the volume, is the same number whether I take the total mass divided by the total volume. Let's say the total mass is m, and then the total volume would be the length times the cross-sectional area. But that's also what I would get if I just take a little piece of it. If I take a little chunk of it that has mass dm and divide it by the volume that that little chunk has. And so this little chunk has length dx and cross-sectional area A. Okay? So what I've said right here is that m is the total mass, which I haven't really labeled on my sketch, but we're just going to let that be the total mass. And dm is the mass in slice dx. This is how we get our relationship between dx's and dm's. I need dm for my calculation. I would rather think of this as sliced up in terms of dx's, so little slices in x. And I can make that relationship explicit by using these two terms here, cross-multiplying. On the left-hand side, after I cross-multiplied, I'd have LA dm, and on the right-hand side, I'd have m times dx times a. A shows up in both sides. It cancels out. Hooray! It had to, because it's something we just made up for our problem. And that leaves us with the relationship that dm is equal to m divided by L dx. So we can replace the dm up here instead with m on L times dx. Now one more thing. What about r? There's no r's in this problem. So how do we handle that? Well, what does r mean here? R means the distance from the axis, is what that's meant. What that means. You're imagining little particles tracking out circles as they're spun around. So if I have a little particle here, how far is it from the axis? That's what this r means. So what variable or combination of variables represents the distance from the axis. In our case, that's x. So if we say x equals 0 over here at the axis, this little point is distance x away, and that's how far it is. This point is a different x value, and it's further. So we just replace x with r. So continuing our example here, we can say that the moment of inertia, which is generically equal to the integral r dm, can be written in our case as x squared, and then we'll replace dm with m on l dx. So now we're going to have an integral in x, and here we have an x, so that's looking good. M and l, that's the total mass and total length, those are constants. We do need one more thing. We need to have limits for our integral. So dx starts at x equals 0, and it ends at x equals l. Let's just look back at our picture to see where that came from. So we start here at x equals 0, and we go all the way over to the right to where x would equal l. That was actually the big reason we switched over to dx's away from dm's, because where do I start and where do I end with dm? I start at particle, I guess, 1, and I end at particle n or whatever, and that's weird. It's kind of hard to visualize what's going on there. Whereas with dx's, it's much more visual to slice something up in the x direction. So my integral is simply ml times the integral 0 to l x squared dx. That's an easy one. That's m on l times 1/3 x cubed, evaluated from 0 to l, is equal to m on l times 1/3 l cubed minus 0. I can cancel out some of this, and I get ml squared and a third, 1/3 ml squared. And a note here, our moment of inertia always has a particular form. Once you're finished with your calculation, it's always going to have the form some number, in this case the number was 1/3, times mass, and not just mass, total mass, times some kind of size. In this case it was length. You can imagine for something round it makes a little more sense to use the radius instead of a length, but some kind of distance squared. It always has that form, and this number, as it turns out, is always between 0 and 1. You can't have, outside of that, you can't have negative moment of inertia. That would be like having negative mass, and you don't get any larger than 1, because that would mean that the average particle had to be further than the total radius away from the center, and that doesn't make any sense. That would be like the object's inside out. So 0 is all of the mass is on the axis, and if all of the mass was truly sitting right on top of the rotation axis, it would be effortless to make it spin around, because you don't have to move the particles anywhere, so they have no kinetic energy, and so they have no moment of inertia. Whereas 1 is the other extreme, which has all of the mass at whatever your distance L was. Whereas our object, this rod here, has its mass spread out, and so instead of getting 0, which would be all the mass over here, or 1, which would be all the mass out here, it's spread out, so we get a number between 0 and 1. In this case, we happen to get a 1/3. Even though you can guess what the form is going to be, to figure out what the number is, what you have to do is integrate. And there really aren't that many problems that are just one-dimensional integrals. Most objects have some three-dimensional bulk to them, and so it's a 2- or 3-dimensional integral, which is beyond the math level of this class. Nonetheless, I can tell you what some common results are, which will pretty much get you through any problem you would need to solve here. So just because these come from integrals doesn't mean we can't tell you the answer. So here are some other shapes to know. All of these are uniform, so these all have constant density throughout. If the density wasn't constant, these results aren't quite right. So let's start with a point particle. It's about the simplest system you could have. In fact, one where you could calculate by hand very easily. Another version to having just a point particle would just be something really small. It doesn't truly have to be a point, but just really small and have that object orbiting around the rotation. Small just means small compared to the distance. So this is our rotation axis. I'll draw all these axes as dashed line. We're distance r away and we have some point. Okay, if that's true, then the moment of inertia is simply equal to mr squared. All right, you just take the definition of moment of inertia with one object. So it's m1 r1 squared, which we just call mr squared. As long as this object is tiny compared to the radius, this is a pretty good approximation. So this might seem kind of silly, but if you think about the moment of inertia of Earth orbiting the Sun, imagine the Sun sitting here. The moment of inertia of Earth orbiting the Sun is equal to Earth's mass times the size of Earth's orbit, or the radius of Earth's orbit squared. Even though the Earth is a really big thing, it's a really tiny thing compared to the size of its own orbit. Compared to the size of the solar system, Earth is just a little speck. Okay, let's look at some other shapes. How about a hoop or a ring about its central axis? Remember, we do need to specify how we're rotating each object. So here's my rotation axis, and I've got a hoop or a ring. We'll draw like a, like a hoop. And we'll say the radius is capital R, and so the moment of inertia is equal to capital M times the, M meaning the total mass, times the total radius squared. Up here we use lowercase because we just had one particle. That's sort of a convention. And then for total mass and total radius we'll use uppercase letters. And we could have actually figured this one out conceptually. Okay, why is the constant 1? Well, in this case, all of the mass is at the same distance from the axis. All of the mass has distance r, and so that's got to be the constant. Let's try one where the mass isn't all at the same distance. We'll do a spherical shell about its polar axis. So like this would be like a hollow Earth. And no, the Earth is not hollow. Okay, so you can see how good I am at drawing circles. All right, so here we are. This has radius capital R again. And we need to have a number less than 1. It turns out that this one gives you 2/3. Total mass times the radius squared. Now you might say, wait, but all of the mass is the same distance from the center. All of it's the same distance from the center, but it's not all the same distance from the rotation axis. Right here, this point is on the rotation axis. This point is pretty close to. Here we're at distance r. On average, we're somewhere in between on the axis and distance r away. To find out that average, you have to integrate, and you would get 2/3 if you carried out that integration. We'll do a few more. Let's do a disk or a cylinder. About the central axis. When I say disk or cylinder, what that means is it doesn't matter how long it goes down this way. It could be a penny, or it could be a can of pop. Anything that has this cylindrical geometry will work here. So the only distance that matters is the radius again. And the moment of inertia is equal to 1/2 total mass times radius squared. I said 1/2 and I wrote 1/3. It should be 1/2. 1/2 mr squared. Okay, why doesn't the length this way matter? Well, the reason the length the long ways doesn't matter is that doesn't have anything to do with the distance from the rotation axis. That's the only quantity that matters. And so that factor, the length, has nothing to do with the moment of inertia. It doesn't even show up in the equation. So this is one of the more common objects. This is any kind of wheel for the most part. We'll have this moment of inertia. Another very common object that you'll see is a solid sphere. We'll do that about the polar axis. So that's the, say like a planet. at least first approximation, because we are assuming the density is constant throughout the whole thing. So, all right, that is a bad circle even for me. Ta-da! All right, I'll just cheat and let PowerPoint make my circles perfect. Except now I can't line it up. Oh. All right. So again, we'll have some radius from the center of this thing. And the moment of inertia for that is equal to 2/5 mr squared. It's kind of a strange fraction. Keep in mind this thing's solid, unlike here where we had the shell. The difference is where the mass is at and how it's spread out. We'll just do 2 more. There are more of these in your textbook. We're not going to do all of them. These are just the ones that are going to show up in any problems that I anticipate you working out. Here we have a thin rod about one end. We just did this example, but we'll include it here for completeness. So this one, we're sure, since we calculated, that the moment of inertia is 1/3 ml squared. And the last one that we will do is the thin rod about the center. So we'll keep the total length as still L. We've just moved where the rotation axis is, and in doing so we changed the moment of inertia. It's easier to make this thing spin because it has a smaller moment of inertia. It's 1/12 ml squared. We could actually figure that out. All you would have to do is use this earlier result and replace L with L on 2. You square it, you get a 4. 4 times 3 is 12. That's how you get a 1/12 ml squared. It doesn't really matter that there's a second side to this. It's just symmetric, so it wouldn't change anything. Now the reason we went through all of these instead of me saying, hey, just look at your textbook, is to give you a bit of a conceptual sense for what things have big moments of inertia and what things have tiny moments of inertia. So the smaller the moment of inertia, the more the mass is concentrated towards the center. An object with big moments of inertia, like say here, has most of the mass far away, or all of the mass far away from the rotation axis. So that's the key conceptual idea, and that lets you estimate, at least crudely, what the moment of inertia of an object is, which then means how easy is it to make it rotate. Alright, so in the next video, we'll look at a slightly more advanced topic with moment of inertia, which is calculating what if we say take our disk and put the rotation axis halfway out from the end. In principle, you can make a table with any permutation of shape and rotation axis, but the thing would be huge. It turns out there's actually a mathematical shortcut to calculating what happens when you move an object's rotation axis without going through the entire integral all over again. So I'll show you that in the next video. See you in a moment.